Hello everyone, and welcome to another session on modeling of finite element in STAAD. I'm Surajit Ghosh, and in this video, I'll cover few advanced method of modeling a reinforced concrete wall in STAAD, which can be transferred to RCDC module for design. There are few rules and regulations for wall design, like shape of the wall or opening. What are those guidelines and how we can achieve that during modeling, that I'll cover in detail. In last video, we have explored few basic options using which we can model a vertical meshed surface like infill wall, create mesh or slab wall connection tool. All these are very simple with several limitations. There are two aspects of modeling a wall. Use the wall stiffness during analysis and design the wall to find the required reinforcement. Using basic option, we can model a vertical wall only for analysis purpose. After analysis, if we transfer the model to RCDC, program does not import the wall geometry or any plate result for design. Another major disadvantage, none of these options identify and maintain proper connectivity with other member and plate, which generates several beam to plate or plate to plate connectivity issue. That's why for any large and complex structure, basic methods are not suitable. By the way, there is no option available in the batch mode to design a concrete wall. In V8i version, there was an option to model a wall using surface element and design it in batch mode. This workflow has been discontinued in Connect Edition. Now we can design a wall only in the Advanced Concrete Design module using finite element result. So if we want to design a wall, we need to model it using finite element with parametric model. For each surface modeled in the physical modeler, whether it is a slab or wall, a parametric model is generated in the analytical modeler. So any vertical wall modeled in the physical modeler can also be designed in Advanced Concrete Design module. Physical modeler has several advanced mesh generation features, like we can easily add any opening or region and modify it later without tampering the analysis model. All these are discussed in part 4 of this series. Modeling with parametric model is the first requirement of design a concrete wall in STAAD. Also, there are several other advantages of parametric model, which are discussed in part 3, like auto-identification of existing member and plate within the boundary, using density point and density line, generation and customization of optimized mesh, inclusion of a region or hole. You can check that video for more details. Today, we will explore how we can use this feature for modeling of a wall. Consider this building which we have modeled earlier in this series. Each floor panel is modeled using a plate mesh and it is generated using parametric model. We can isolate the top floor of the building using view management tool and review the meshing quality. All existing member and nodes are considered in the mesh, and generated plates are adjusted to establish proper connection with the existing element. Till now, there is no modeling issue. Now I want to model couple of boundary walls and a central lift core at this location and design the wall. So basic methods are not suitable. Also, it is very hard to maintain proper connection at the wall slab junction between new and existing surface. Slab wall connection tool is of no use due to multi-level surface. Best option is the parametric model, which can generate a mesh considering all boundary condition. By the way, without even modeling the floor panel with plate mesh, we can consider the in-plane stiffness by modeling it as a rigid floor diaphragm. But we need to design the slab using moment coefficient method, which does not provide optimum reinforcement for a complex geometry or slab with cutout. Design using plate result is more accurate, and if required, we can design it as a flat slab or post-tension slab using Advanced Slab Design module. That's why for this building, modeling of floor diaphragm using FEM is my first preference. Modeling and design of flat slab will be covered later in this series. Let's start with the periphery wall. One suggestion, try to use the view management tool during modeling Using this, we can save or generate a view of the structure anytime for modeling or result interpretation. During mesh generation, I want to cross-check the connectivity of wall with existing slab. So few layers of plate are included in this view. Now we can simply add a new parametric model and define the boundary of the wall. If there is any existing beam or column, that helps to identify the boundary. Later, after mesh generation, we can remove any unwanted member. Next, select the surface and element type, provide a target element size, and generate the mesh. Once this primary mesh layout is generated, we can cross-check the connectivity and meshing quality. If required, change the mesh size to finer or coarser, and then finalize it. See, all existing node of floor panel and members are considered during mesh generation. We don't have to count or provide the boundary division to maintain the connectivity. It's not only for a single layer, but all existing floor panels are considered during wall generation. If we want to generate a mesh connecting multi-level surface or member, parametric model is the best option. Using same approach, we can generate the lift core, which is a combined wall with 3 separate surfaces connected with each other and also with all the floor slab. None of this wall has any beam to plate or plate to plate connectivity problem. We can confirm it using the tools available in the utilities page. I always prefer parametric model for mesh generation as the meshing quality is far better than any basic method. After analysis, we can transfer this model to advanced concrete design module where the analysis results are used for beam, column and shear wall design. You can check my previous video on concrete design for more details. We can initiate the wall design with this option, following any available design code including IS 456. Program internally reads the analysis result from STAAD file along with the supported entities and generate the design model. In this model, walls are modeled using parametric model, hence all are imported, and we can design individual shear wall or the combined lift core wall using FEA result. In RCDC, multiple interconnected walls are considered as combined wall, though each wall is designed individually, neglecting the combined action. For the overlapping zone, maximum reinforcement is provided considering the design result of both walls. By the way, if the model is modified, we can reanalyze and use the modified force to update the design result of linked RCDC file. During update, program redesigns all the column and wall and report whether there is any significant change in the design result or not. Easy, right? Though this interconnected modeling and design features looks promising, there are few limitations of wall design that we need to keep in mind during mesh generation. One such limitation, RCDC cannot design a shear wall with opening. If we model a wall using parametric model with an opening, we can easily transfer that to RCDC, but program designs the entire wall as a solid surface without considering any opening. Check the elevation view of this wall. No opening is considered in the final design. Also, continuous reinforcement is provided in the entire wall. If the opening is small, we can neglect that and use this approach to design the shear wall, though design results are not that accurate. But for any large opening, like a glass cladding in the lift core or opening for door, it is not a correct approach. If there is any opening in the wall, additional reinforcement is required like the coupling beam with diagonal reinforcement, which increase the lateral stiffness of the wall and help to resist any lateral force by combined wall action. This is not considered in RCDC during shear wall design. For large opening, it is better to model the walls separately as individual strip. To model this wall with opening, I have used 4 separate surfaces, 2 vertical strips and 2 small horizontal strips. We can design the walls individually in RCDC and then create a group for uniform reinforcement. Until the opening and extra reinforcement for coupling beam is considered for design, this can be used as an alternative approach. RCDC can import the analysis result and design any shape of parametric wall, whether it is a rectangular wall or other shape. I know this type of wall is rare. This is just an example. Also, it is better to divide such wall in regular strips, which provide more accurate design result. Finally, any surface which is not purely vertical, like an inclined parametric wall, is not considered for design. RCDC can read the wall information only if it is in a vertical plane. Any inclined wall is rejected for design. There are few other rules, but those are not very important. If we want to design a shear wall in STAAD, during modeling, we need to follow this guideline and select the most suitable approach. Accuracy of design result depends on modeling. Rules for tank wall design are different. That's all for today. Thanks for watching.